Alright guys, welcome back to the workshop. If you are watching this, what am I even saying? If you're watching this as a video after this live has already finished, then feel free to skip ahead a little bit to the content, because I'm just going to be waiting for my audience to kind of jump on, and we'll be looking at this. This is a Korean clone of the Soundigital circuit, not a Chinese clone. This is a Korean clone. So I'm just going to wait for my live audience to jump on, and then we'll get started. So like I say, if you're watching this back later after the stream is finished, then feel free to jump forward to the content, which should be about 5-10 minutes or so. How's it going, guys? Good to see everyone. Just gonna wait for this to pick up a little bit. Yeah, you weren't first, Jason, I'm afraid. Thomas was first, followed by Lowry. Lowry's usually first, but he was slacking a little bit today. Just make sure all of the cameras are working. Yo, yo, yo. What's up, sine wave? Let's just remind myself where some of these parts are on here. Rail. I think the rail is over here, yep, and then that's the voltage divider with the 102, and then do we have something similar for the 12 volt side there possibly? Ground, and I think it will be this one. That's CC. That one. Okay, cool. So guys, how's it going? Afternoon. It is a Sunday afternoon here in the UK. Freezing cold outside. And we are going to be looking at this. This is a full bridge amplifier. It is a Korean built amplifier, even though it looks like a Brazilian. And the reason it looks like a Brazilian is because it is a Korean clone of the Soundigital circuit. So this circuit layout is Soundigital's original kind of layout that they made years ago, and it's been copied by China, and now it's also being copied by Korea. Now, I don't know whether this Korea copy is a copy of the Chinese copy of the Soundigital, or whether this is referenced originally back to the Soundigital, but this thing is a freaking mess. This has a bunch of issues that make it really, really unoptimized and just terrible. And we're going to go through and we're going to see why it's so bad, what's wrong with it, and see if we can correct any of these poor factory optimizations. No, Larry, it's terrible. It's very, very bad. Good to see all you guys. Yeah, thanks for jumping in. So, the first thing that I'm going to show you is a fault with the amplifier, a design flaw with the amplifier that doesn't even require us to turn it on. So, what we are going to do though is put some power wires in. So, we're going to connect some power leads, 12 volts and ground, of course. Let's do that for you real quick. Good to see you, Boris. Thank you very much. Okay, there's ground, there's power. Now, I'm not even going to connect the remote wire. I'm just going to leave this floating for now, alright? So we're going to turn the power supply on. Now, because this power supply is a little bit uncalibrated, it's going to show 0.1 amps of current draw even when there's actually no current draw at all, just because the current meter is a bit uncalibrated. I need to sort that out at some point. So just pretend that this says 0.0, okay? So as we increase the voltage, obviously we're now at 9 volts, we're now at 10 volts, 11, 12, 13, 14, 15 and 16. Okay, we now have 0.2 amps of current draw, bearing in mind the remote is not connected, and if you notice with the keen eye, you will have seen that the fans on the board started spinning, which is very strange. Why are the fans spinning? We haven't even applied the remote yet. So this means that there is always going to be some parasitic current draw from this amplifier, even below 16 volts. When you go below, I think it's like 14, go 14.2, the fans are still spinning a little bit there. Let's go down further, 3.8, one of the fans is still spinning, 3.5. So yeah, below 13.5, the fans do stop, but that doesn't mean that there isn't still voltage potential across the fans. If we have a look at the multimeter here, put it to voltage mode, if we go across the connections for the fan, you can see that there is actually 1.97 volts there. So there is the board is still trying to power the fan, but it's just not high enough voltage to make it spin. And as we increase the voltage a bit more, on up to 16 volts, we now have sort of 4.6, 4.7 volts, 5 volts there across the fan, so that's why it turns on. So basically, if you were to connect this to your vehicle, it would be very, very slowly draining the battery the entire time, because there is energy going through the coil windings for these fans, which obviously is very bad. So that's our first design flaw, and I actually spent a little bit of time the other day looking at where's this voltage coming from? Why is there voltage going to these fan connectors, even though, you know, we haven't even applied the remote yet? And basically, the issue comes from the MCU. So here we have a microcontroller, which all of these amplifiers have, and this is programmed from factory with specific firmware for how they want the amplifier to behave. So obviously on pin 1 we have VCC, which is about 5 volts on pin 1, supplying power to the MCU. Now the MCU also gets fed with some reference voltages from elsewhere. I'm just noticed for a second there a little bit of, oh no, I thought that was a bit of solder, but actually it's just part of the board. This MCU is fed with reference voltages. It's fed with 2 main references which are present even when the amp's not powered up. It gets a reference from the rail voltage, okay, so obviously the rails may be up to 200 volts, and there's a voltage divider here consisting of these 3 resistors, and the MCU is fed with that low voltage after it's been reduced by the voltage divider, so the MCU knows what the rail voltage is based on a reference. So that is always going to be there. The MCU is also fed with a reference voltage from the power terminals, which is fed from this voltage divider right here. So what it looks like is happening is that voltage is making its way through the MCU back out of the 5 volt VCC, which is then working its way back through the circuit, and it's activating and energizing some transistors which are responsible for turning the fans on. So we don't have the remote connected at the moment, but let's just have a probe with our multimeter, our oscilloscope, and let's see what voltages we have at the MCU. I'm going to turn it up to 16 volts, which is where the fans start to spin. So you can see that, well, yeah, the fans are now spinning. Okay. So on VCC we currently have 2.6 volts. Okay. So that's why the fans are on, because that voltage is being fed back down through the circuit. But what's on some of the other pins here of the MCU? We have a little bit of noise there from the fan oscillating. You can see that. So if I stop the fans now with my hand, oh, that noise actually is still there. So yeah, so I guess this is kind of the MCU trying to come to life, because obviously we've got like 2.6 volts on the VCC of the MCU, so it may be trying to come to life and trying to do stuff. So we've got this waveform on the MCU here, one of these pins. Let's just try another pin up here. That one's nothing. That one's nothing. This one here is 1.5 volts. 1.5. 2.2. That doesn't seem to be anything. Nothing. Okay, we've got 3.3 volts there on this pin right here. 3.3 volts. Is that coming through the voltage divider for the let's have a look for the rail? Okay, not quite. Is that coming through the voltage divider for the main supply? 2.2, no. So we've got 3.3 volts here on this pin. And I could look and try and figure out where that's coming from. But that's going to probably be what's causing there to be some voltage on the MCU, on the VCC pin. Let's have a look at this pin. We've got 3.0 there. Nothing on that one. Let's have a look on the other side. So that's VCC, 2.6. Nope, nothing there. Nothing here. That's a little waveform from the MCU trying to do stuff, because it's being partly powered. Again, another one there. Nothing there. 0.6. There we've got 1.2. And there we've got basically nothing. So the highest voltage on the MCU is actually this fourth or third from the end pin? This third from last pin here. This is where we've got 3.3 volts. So that's likely where the energy is coming from, which is energizing the VCC pin over here, which is causing the fans to spin and the circuit to sort of start to want to come to life. So we don't have a trace coming from this pin here, but we could have a look and see what else has 3.3 volts on it elsewhere on the board. So let's do a continuity check. So it's this third pin from the end, this one right here. Let's turn the power supply off, and that's going to dissipate. Dissipates quite slowly, so it might be to do with rail voltage, because yeah, so you see how that voltage is mostly still there. I think that's going to be rail voltage related. So we still have 15 volts on the rail, which is right here. But on the 12 volt terminal, we only have 2 volts. So we still got like 15 volts on the rail. And on this pin here, let's turn the power supply back on. You can see 3.2 volts. Now if I turn the power supply off, this voltage very, very slowly sinks down. So I think that's going to be referenced to the rail. So with that in mind, let's have a little probe around on continuity mode and see if we can see what is connected to the MCU on that pin, and maybe we can fit some kind of, I don't know, but I think this is going to be an issue in the MCU itself. Right, what are you connected to then? Pin 3 there. Where do you go? Okay, we've got continuity to this resistor right here, R115, which is a 332. So let's see what's on the other side of that resistor, and if the voltage is higher on the other side of that resistor, then obviously we keep going. If the voltage is lower, then that's where we stop. So here we have 3.3 volts. On the other side we have 0 volts. Okay, so that's not where we're going. That's not where the voltage is coming from. Let's continue and see what else is connected to that pin. So now we have a nice place to put our multimeter probe here on this resistor. Let's go ahead and just scratch away, see if we can find somewhere else that has continuity to that pin. The capacitor there. Okay, here we go. 472, this is R53. We have continuity there. So let's see what's on the other side of R53. 3.3. Aha! So on the other side of R53, we have 16.3 volts. And that is our power supply voltage. And that is connected to the power supply. So that means that this resistor is acting as a step down, like a voltage divider, so that the MCU knows how much voltage is on the power terminals at all times. Okay, and that is making its way through the MCU out the VCC. So there's not really, I don't think, anything we can do about that. Because obviously the MCU needs to know how much voltage is on the power terminals in order for it to work. It just seems to be maybe an issue with the firmware in the MCU, which is causing the voltage to come out of the VCC. I don't think the MCUs can be damaged because this is a brand new amplifier. Let's have a look at one of the Chinese clones of this circuit, which I don't think exhibits this issue. I've got one of those in the loft and I want to see, is that resistor network set up the same? Unfortunately, I don't have a spare MCUs from any of those boards because I've already stolen them, I already nicked them and used them. And also the MCUs are different packages, they're slightly different sizes. But it would be interesting to grab one of those boards that's been on fire, so it can't be fixed, and just have a look and see what the layout is like differently. So bear with me a sec, I'm just going to pop in the loft and have a look. And we'll see what we find. Okay, so here we have one of the it's basically the same circuit, okay? But it has a different MCU. This one is, I think, was this the Sundown or was this the Def Bonds? I think this one was the Def Bonds. So this is the Def Bonds amp that caught fire, and it unfortunately has a different package MCU, so I can't swap them over to see if that helps. But I can see whether we have a similar setup there. Let's just read a little bit of live chat while we're back. Thank you very much, Sandro, for the 2. That's very kind of you. Thanks for your knowledge you spread. No problem at all, man. I really appreciate that. Thank you so much for your generosity there. I hope you're having a great day. Afternoon, everyone. 8-bit PIC family are pin 8 ground, pin 16 VCC. So yeah, these ones have VCC on pin 1, it looks like here. Pin 1 is definitely VCC, pin 16 is not. It's a common microchip 8-bit MCU, perhaps it's missing its ground. I don't think so, because the amplifier does work. It does function absolutely correctly, so I doubt it's missing a ground, and I think I did check that. Yeah, one of these pins definitely has ground on it. So what I want to do is I want to have a look at this, which is the one that was on fire, which is the same kind of circuit, but it does have a different package MCU, but I want to see whether there's a similar setup here. So, okay. This here is VCC, this one here for the MCU, okay, and that's pin 1. So we have basically the same sort of pin layout there. Now what pin was ground on this one? Ground on this one is okay, pin, whatever the last pin is, the last pin, pin 20 maybe, is ground. So let's see whether that's also the case on this one. Yes, it is. So I believe this to be the same MCU, just in a much larger package, which is frustrating. It would be nice to be able to swap it on there, but unless I, you know, have some kind of wacky, crazy surface mount riser board thing fitted, I'm not going to be able to put that on there, which is a shame. You could put that on there, because you could probably get, you know, a daughter board that fitted the smaller chip on the bigger pads, but the bigger chip on the smaller pads, that's going to be a mission. So let's just see. So the third pin from the end on our main board was coming from a voltage divider from 12 volts terminal. So let's just see whether that's sort of going to be present around here, shall we? What have we got? Okay, so we've got something there. We've got connection there, and then on the other side of this resistor, do we have connection to the 12 volt terminal? Well, we don't, but that might be because it's missing from these traces. It's one of these traces here that's floating, so I suspect that probably was 12 volts from the 12 volt terminal. So yes, we do have the exact same setup here, and I don't believe that this amplifier had that issue. So I suspect that it might be a problem in the firmware, perhaps, for this MCU, which is causing the leak of voltage through. Now, what can we do about that? Obviously, this MCU needs to know what voltage is on the power terminals at all times. So we can't really remove that. I guess we could remove it and give it a fixed reference voltage based on the VCC here when that comes alive. But that would mean that we get rid of any low voltage or over voltage protection on the power terminals. And with an amplifier this size, it's probably quite important. But that is an option. We could remove this resistor, and we could just feed the MCU with a fixed voltage reference based on its, you know, taken from its VCC supply when it comes alive, when the remote is active. The second option is to just allow it doing its thing, but just put a 4148 diode in series with the VCC pin, so that, okay, yeah, when you're connected to 12 volts, this thing is going to still try and come alive, whatever, but at least it won't be backfeeding to the fans. So out of those two options, I think I'll probably just disable the chip's ability to read voltage from the power terminals. I think that would be the best thing to do, rather than cutting the trace. And because if we cut the trace for VCC, then the chip is still trying to come alive. It's just not backfeeding to the fan, so it's still going to draw current. Whereas if we just remove this voltage divider from 12 volts, then that should prevent that issue. So just to test the theory. So if I go 12 volts here, that resistor there. So let's lift this resistor, R53, and let's see whether by lifting this resistor that prevents the fans from coming on before we've applied the remote. Greetings from hot AF South Florida. I'm very jealous, man. I'd love for it to be summer, hot time here. It's freezing. I hate it. I hate the winter time. Sean says I just received the 16K version of this. They suck, man. These are some of the worst circuits on the market at the moment. Diode in series to the VCC will cause the PIC internal reference voltage to change, which will offset its protection bias. So yeah, if the VCC going into the chip is a little bit lower, then that might cause that, yeah. That's a good point. So the issue isn't that the fans are coming on. Like, obviously the fans being on isn't great, but the fans coming on is a resultant of the problem. The fans being on isn't the problem. I could just route the fans to the other connector, and then that would stop them coming on. But what that doesn't stop is that doesn't stop the parasitic current draw of the circuit trying to come alive. The fans being on is just a sign of that, if you get what I mean. So what we need to do is we need to correct the problem at the cause to stop the circuit trying to come alive without the remote being present. Because yeah, even if I reroute the fans somewhere else, yeah, okay, the current draw goes down a bit because it's not spinning the fans, but the circuit's still trying to turn on. And that's not a good state for it to be in at all times, you know. So we're going to try and correct that issue at the source. So with this resistor lifted, we might actually lose VCC completely, because it might be generated from that 12-volt reference there. Although I doubt it. It's probably coming from somewhere else. Right, so let's turn the power supply back on, and let's have a look and see whether... Okay, so 16 volts is going in. The fans are not spinning, I can confirm. You can't see that, but they're not spinning currently. And we don't have any voltage on VCC. That's great, excellent. Obviously we don't have any voltage anywhere else. There's no strange waveforms on any of the pins of the MCU here. Fantastic. So yeah, that was an issue. We could correct that by linking some kind of circuit to the remote wire that then allows the MCU to see the battery voltage after the remote is applied rather than at all times. That would be a good fix. Okay, I'm curious now then, if we apply the remote, does the MCU get its VCC, or is that coming from somewhere else? So let's just tack the remote wire onto there like that. So let's go ahead and, so obviously we can turn the voltage down from 16, doesn't need to be that high. That was just to see if the fans came on. Okay, there we go, just stay at 10 volts for now. So let's probe VCC to the MCU, and what do we get? Okay, wrong camera, wrong foot pedal. Where's my foot pedal? Here it is. Okay, we do get VCC, yeah, we get 5 volts. So that resistor isn't necessary for the generation of any supply voltages or for the amplifier to come on. That is just a voltage divider for the MCU to know how much voltage is present on the terminals. Cool. So based on that, what we could do is we could create a new voltage divider that sends sends VCC, which is 5 volts, through to this pin or this pad here, and that would maybe bring it down to like 2.5 volts, and that would just make the amplifier believe that there's the correct voltage on the power terminal at all times. Now, just for the time being, I am going to put that resistor back, because I don't think the amplifier is going to probably come alive and turn on with that resistor missing, because it's going to think there's not enough voltage on the power terminals. But let's just see, do we get any power supply switching on the FETs with that resistor lifted? Let's see. No, we don't. The amplifier is just flashing the blue LED because it thinks there's no voltage on the power terminals. Of course, because we lifted that resistor. Okay, no worries. But what I'm going to do is I'm going to put it back, just for now. Now at least we know where the issue is and what we need to do to sort that little problem out. I'm going to put it back and show you the rest of the problems, the rest of the design flaws with this thing. Because it's not good. And we can sort that out later. Right. So with that fitted back in place, the amplifier will now turn on. Now what I'm going to do is I'm going to show you how this amplifier behaves at various different input voltages, from 10 volts, 9, 10 volts, 12 volts up to 14.5, 15 volts, because it's very interesting and very unusual. In order to do that, I'm just going to drop a load across these speaker terminals. Big janky Class D amps like this do not like being idled, without a load across the speaker terminals. So let's put a load across the speaker terminals, just for safety. There we go. Make sure there's no random bits of solder anywhere inside the board before I power it up with high voltage. Safety glasses on, as always. So let's get this thing to life then, shall we? Now when we power most amplifiers like this, when you power them up, there will be some kind of health check mode at first, where it sends very low duty cycle pulses to the power supply MOSFETs at first, just to build a little bit of rail voltage. The MCU will then detect that there's rail voltage being built and then allow full power up. In the case of a failure or a short circuit on the output side, obviously rail voltage won't stay being built, it will just be shorted to ground. The MCU will detect that and it will stop the amplifier from powering up. So in this case, with this amplifier, when we apply the remote, let's have a look at what we get on the power supply MOSFET drain. Yep, we get some tiny little health check pulses, which look a little bit like this. They're very, very tiny, so the scope has a pretty hard time making them out, but they are present. And every time it does that, it's going to build a little bit of rail voltage. So now, if we look at the rail voltage, you can see on the scope we have 54 volts worth of rail. So every time we apply the remote, it's going to build a little bit more rail voltage like this. And then it's going to try and build the rest of it, drawing high current from the power supply, which you should be able to see up here. So let's allow it to build full rail, and we're allowing 12 volts into the amplifier at present, okay? And we're going to probe the low side drain of one of these sides to see the Class D switching come alive. So let's continue with the full power up. Okay, there we go, we are alive. We have a Class D switching frequency of 135-ish kilohertz. It's a little bit wobbly, it's not the most stable frequency ever. It's quite spiky. We have big spikes here at the start of the on phase of the rail there. And it's the same on the other side of the board as well. A little bit less spiky on that side actually. We've got a few more spikes on this half, but it's pretty similar. Now, if you have a keen eye, you'll notice the power supply kind of doing all kinds of weird stuff. The constant current LED is illuminating sporadically and the current is all over the place. And that's because this is a regulated amplifier. So the power supply is holding the rails at a specific amount. So if we probe the power supply MOSFET drain, this is currently what we have. We have very low duty cycle pulses on the gate. If we have a look at the gate, see this is what we got on the gate. Very, very, very low duty cycle pulses. It's just kind of topping up the rails and keeping them at a specific predefined voltage. And to do that, it's just doing tiny little pulses to keep the rails topped up. And that's what that looks like on the power supply MOSFET drain. If we look at the rail voltage itself, it's currently holding the rail at 151.5 volts there or thereabouts. So that is the regulated rail voltage of this amplifier. You can see if I turn the voltage down from 12 volts to 11 volts, we're still at 151 point something ish volts there. The power supply is still regulating, as you can see. If we go have a look at the power supply FETs again, yep, still regulating. If we go down even further to 10 volts now, ooh, okay, we had a lot of current draw there, and I'll explain why that was in a minute. But let me just turn my current limit up a little bit. Let me just turn my current limit up to about 14 amps there. So we're going to go back up to 11 volts here. Wait for the amplifier to come alive. There we go, amplifier's alive. So like I said, we're regulating, still at 150 volts. Now, if I go down 10.4 volts, we're still at 151 volts worth of rail, so we're regulated. Let's go down even further. 10.1, there we go, and 10 volts. So now we're at 10 volts. We're still at 151 volts worth of rail voltage. Let's have a look at the power supply FETs. They're still regulating, but the duty cycle is a lot higher. Look at the gate pulse. The gate pulse is now a lot higher. You can see here, if I try and lock into that, why are you not locking in? There we go. So the duty cycle is now at about 14% and it's varying a little bit. So we're still regulating, we're still not going full duty on the power supply. and we're still holding that rail voltage at about 151 volts there, but the power supply is having to work a little bit harder to keep it there. What you'll find is interesting is that the idle current draw with this amount of low duty is 6 amps. That's very high. Considering the power supply is barely working at the moment, the power supply is not doing anything, it's just, 14% duty cycle. 6 amps of idle current draw. It gets even worse. If we decrease the voltage further to bring the amplifier fully out of regulation, as I decrease this further, you'll see duty cycle is increasing further. 9.8, 9.7. See, now the duty cycle is up at about 20%. 10 amps or 12 amps of idle current draw. The amplifier's not doing anything. Let's turn the current limit up even further, because I feel like this is going to go to the moon. Let's decrease the voltage even further here. 9.4, 9.3. So now we're at 48% duty. So basically now the amplifier is not regulating anymore. The power supply is trying its hardest to keep the rail at 150 volts, but it's no longer able to. 48.2% duty cycle is now full duty, so the power supply is maxed out. If we have a look at the rail voltage is now sitting at 148, so that's why the power supply has gone full duty, because it's trying to get that back up to 151, which obviously it can't because we don't have enough voltage going into the amplifier for it to do so. But guys, 11.3 volts, have a look at, right, so this is obviously the gate waveform. We've got 48% duty cycle there, 48.1, 48.3% duty cycle. Look at the drain waveform. Look at the state of that. That, my friends, is hard switching. Like, absolutely ludicrously hard. Look at this big spike. Look at that monstrous spike on the drain there. That is going up to, that spike is 40 volts high. That's a 40 volt spike there on the drain of the power supply MOSFET. And the reason for that is because the MCU has been programmed with barely any dead time. So what that means is, that there's not enough time, there's not enough of a gap between bank A turning off and bank B turning on of these power supply FETs. So there's immense cross conduction. There's a small period of time where both A and B banks of those power supply MOSFETs driving the transformer are both on at the same time, and that looks like that's what's causing that big spike there. We can confirm that by grabbing both of our oscilloscope probes here and having a look at both banks of gate waveforms here. So I'm just going to hold that on there on bank A and hold that there on bank B, and let's see if we can see the cross conduction on the scope. I haven't actually tried this yet, but I suspect we will be able to see it. So let's turn channel 2 on the scope. Let's power back up. Okay, that's in phase for some reason. We need it to be not in phase. Is it this bank here maybe? Do I have one of these inverted? No, I don't. Ah, here we go. There's only 2 FETs per transformer, that's why. Okay, so it needs to be on those 2. There we go. Okay, so here we have the power supply gate waveforms. Now, here we have a bit of noise, which I probably not going to be able to get rid of. But can I go with that one? No, DC couple, AC couple, reject high frequency. That's the best we're going to get it. So this is the power supply gate waveforms, okay, together. And as you can see, there is a pretty big overlap here. Well, actually, there's not. It's a very mild overlap. Actually, it's not that bad. Right there. Let's go and look at the other one. Let's go. Aha! This is probably where it is. Yeah. So as you can see here, there is an overlap where this MOSFET isn't fully turned off, but this one's coming on. So there's not enough dead time there, and as a result of there not being enough dead time, there is a huge amount of current draw and we're getting that big spike on the MOSFET drain. Now this is just me speculating. This is just what I believe to be the issue here, okay? This isn't absolutely for 100% sure the issue, but this is just what it looks like is happening. But we can confirm, we can find out if that's actually the case by doing a little modification to the board here to see if the idle current draw improves, to see if it lowers. So normally what you would do is if you've got a switch mode power supply like this and you've got not enough dead time, or the amplifier, the board is so hot that what the fuck? This, right, bearing in mind, switch mode power supplies on amplifiers should run stone cold at all times unless current is being drawn because the amplifier is playing into a load. This amplifier is not being played into a load. There's no RCA connected. It's idling. It's idling. And the heatsink is very warm along the power supply side specifically. It's actually kind of warm even across the output side. But the output side, you're likely to get a bit more cross conduction because of the higher voltages, faster switching. So for output MOSFETs to run warm at idle, yeah, it happens. You know, maybe it's not the best optimized circuit, but it happens. For a power supply to run hot at idle is absolutely barbaric. So that we do need to correct this. This is very bad. So usually what you would do in this instance is you would fine-tune your oscillator, your PWM generator, might be a TL494, might be an SG3525, whatever the case may be. You would fine-tune the parameters on that with external capacitors and resistors to increase the dead time a little bit. To just give the FETs a bit more time to turn off before the next bank turns on. However, in this case, we can't do that because we've got an MCU. So this has been programmed at the factory, so it's probably locked. I don't have any of the hardware or software to reprogram these MCUs. That's not something that I do. I just, on a component level repair technician, I don't do programming. So I can't correct that at the source. The best thing that I can do is to either change some of the gate drive circuitry to kind of make there be a bit of more of a delay between one FET turning on and to speed up the turning off of the other FETs. Or I can instead possibly put some kind of MOSFET driver in between the MCU and the final drive buffer, which has programmable dead time, so I can then set some dead time for it. However, it could not necessarily be a dead time issue. It could be just some issue with the frequency, okay, that the MOSFETs are oscillating at, not being optimal for the type of transformers used. So transformers will have like an optimal range of frequencies that they want to be switched at from an from a switch mode power supply. And if you switch too fast or too slow, then basically it doesn't work, it breaks down and you get this big current draw. You can get these great big spikes on the drain of the MOSFET there. It's like a bit of a flyback effect perhaps. So that could be another reason why this is unhappy. And we can't really change the frequency very easily. We can replace the MCU's oscillator with something like a TL494. We can retrofit a TL494 in place of the to drive the power supply instead of using the oscillator inside the MCU. But that takes a little bit of work to get that integrated nicely into the circuit. So it's either going to be lack of dead time or it's going to be incorrect frequency. And the quickest one to test first would be lack of dead time. In order to see whether it is lack of dead time, one thing that we can do is we can modify the gate drive circuit. So over by the MOSFETs here, the gate resistors are 10 ohms, okay? So that means that the energy from the driver has to pass through the 10 ohm resistor, which is a little bit slower than just a trace, before it gets to the gate. And then when the MOSFET is being asked to turn off, then it has to be pulled through the resistor as well. So the turn on and the turn off is slowed down a little bit by the gate resistor. So what we want to do is we want to widen the gap between the on and the off. So if we lower the resistor, well, that will speed up the turn on and it will speed up the turn off. So that doesn't really help because that's probably just going to make things worse. If we increase the gate resistor, well, that's going to slow down the turn on, which is great. That might give us a bit more time, but it's also going to slow down the turn off. So any gains from any gap that we make is just going to be nullified by the fact that it's now slow to turn off as well. So one thing we can do is we can fit a higher value gate resistor to slow down the turn on, and we can fit a diode across in parallel with the gate resistor, so that when the drive circuit asks the FET to turn off, then that energy can bypass the gate resistor through the diode instead, which will be seen as a low resistance. So we go higher resistance, turn on, low resistance, turn off, and that should hopefully widen the gap a bit, give us a bit of dead time to stop these from cross-conducting when they're at full duty. So yeah, I'm not sure which one it's going to be. Fitting new gate resistors and parallel diodes across all of these is going to take a little while, for about half an hour. So I don't know whether to do that and see whether that sorts it, because it might not, and then I will have wasted my time. But let me know what you guys think. There are some very intelligent people that watch these streams and videos, so what would you do? What's your thoughts on that? Let's have a little read of some live chat while we're here. Nope, camera's the same. Did no one test the thing before shipping? We haven't even got to the well, we've seen two design flaws so far. Obviously, we've seen the MCU backfeeding the VCC issue, and we've now also seen the horrendous ringing and cross-conduction high current draw on the power supply FETs. This definitely wasn't tested. This has been slapped together in a ridiculous hurry. Yeah, this is one of the worst that I've ever seen come out of a factory. Since remote is usually just battery voltage, why don't you just hook that up to the voltage divider to the remote? Yeah, that is another possible solution that we can do. Instead of using, yeah, we can either do that, or we can use the VCC 5V reference. It would be the same result. Yeah, it'd be exactly the same result, because the VCC appears as soon as you apply the remote. So we can either use the 5V that appears when the remote's applied, or we can use the 12V that appears when the remote applies. I don't personally like connecting anything from the circuit to the remote wire, because in the event of some kind of failure inside the amplifier, if there is some connection to the remote wire, that can also kill a head unit, and head units can be bloody expensive. So I like to keep the original remote circuit intact, because the original remote circuit will be buffered. It'll be very, very much detached from any part of the circuit that could fail, that could backfeed down the remote wire. So I'd prefer to keep it that way. And if I need some part of the circuit to activate based on the remote turn on, I'll take it from a reference somewhere else that's not then going to feed back down the remote wire in the case of a failure of some kind. So this amplifier is not branded. This is an unbranded, I guess it's a prototype. The customer for this amplifier purchased it directly from the Korean factory. Okay, so it was a factory direct, kind of like, you know, Alibaba kind of thing. You know, it's just a Korean factory direct. So there's no branding on the amp at all. It's just a black heatsink. And like I said, this is a Korean clone of the Soundigital circuit. It's not a Chinese clone. It's not like the Chinese ones that you see from Sundown SFB, Ground Zero GZCA, Def Bonds Apocalypse, all that. It's the same circuit, but this one has been done in Korea. And it is absolutely dreadful, as I'm sure you've worked out by now. is there a way to disable the no sound standby on Class D amps? I have a pair of studio monitors that like to pop when coming out of no sound standby. The pop will probably just be Class D initializing, so unless you fit a relay, there's no way to really get around that. You can also get higher quality effects with lower input capacitance. Yep, I'm not changing all these effects though, they're fine. Would you ever go live with Living Loud with Andy? I don't know, I haven't seen any of that creator's content, so maybe? Are these what I've been seeing on Alibaba recently? Possibly, yes, although Alibaba is typically Chinese. This one is made in Korea. Maybe there's a supplier on Alibaba from the Korean factory, I don't know, I haven't seen it. If your amplifiers get damaged from inductive kickback from solenoid-based battery isolators, no, I haven't seen any amplifiers get damaged from that. You do get amplifiers get damaged from jump starting another car, like if your car or if another car is being jump started. I've seen amplifiers get damaged from that. What's your thoughts on the Teramis Big Boss 3 circuit? I like it so far. I haven't done any like super heavy load testing with it though. A few reports from some of the UK guys here are saying that the Big Boss 3 is noisy. It's a noisy amplifier. By that I mean there's a lot of distortion on the actual output of it, which I haven't tested for because I haven't actually load tested it. I've just looked at the circuit on idle. So I'd like to load test it and see if I also see that and see what that's all about. So I can't comment on it at this time because it's possibly not great. Oh, can you get the live chat on screen? Oh yeah, usually it should be on screen. Sorry about that. Where are we? There we go. Yeah, sorry. For some reason it hadn't initialized. I heard some speculate that many amps from Ali and similar are amps that didn't pass quality control. Yep, that's very possible. That's where they're all going to end up. So with this specific fault, I think what we're going to do is we're going to fit some higher value gate resistors and some 4148s in parallel across the gates. It's going to take me a little while, and I'm not actually even sure if I've got enough 4148s. So I need some surface mount ones. Let me just check if I've got enough of those. Because if I don't, then I'll do this mod on another stream sometime. But I wanted to show you guys that we haven't got to all of the design flaws yet, by the way. We've seen 2 of them so far. The next design flaw, I wouldn't go as far as to call it a design flaw. Possibly, it's a strange design choice. It doesn't make sense why they would do it in the way that they have, and I'll show you that in a minute. So yeah, I'm just checking to see whether if I have a whole bunch of surface mount 4148s that I can use to change the drive circuitry on the power supply. Opinions on the best quality, most reliable big power full bridge amps on the market currently. Paris 15K, PW 15,000, absolute monster. OP. I think these are these 4148s? OP. OP SMD diode. What do we get? Screen. So apparently it's a Zen diode. OP. Don't remember ordering Zeners, but I guess maybe it is. I don't want to put a Zener in place, that won't do well. What are these ones? W1. What's W1? W1 is also a Zener? Zener, you guys call it a Zener diode. There's no 4148s in there, so that's not probably going to be a 4148 either. Well, I've used a lot of these. It's very strange. So yeah, I think I need to order some more 4148s before I can do this mod and be happy with it. So I'll do that. But let's move on and let's show you what the next strange design choice is with this thing. Because it's very strange. So, as you've already seen, gents, the power supply is regulating the rail voltage to 150 volts. So the components on this board are all rated for 200 volts as their kind of breakdown voltage. We've got 200 volt rail caps. We've got IRFP 4427 output FETs, which are 200 volt. I think they're avalanche rated, but you don't want to be going any higher than 200 volts. We've got IRS 2957S drive ICs, which are 200 volt rated. So everything has basically a ceiling of 200 volts in this amplifier on the output side. And we're regulating at 150 volts. Now, I like to be safe. I like to have a safe head window, headroom above the breakdown voltage. But 150 seems a little bit on the low side for me. So watch this. Watch what happens. Now, you've seen this amplifier powered up and regulating at 150 volts with 12 volts worth of input voltage. Okay, so turn it back on. So we're going to start here at 11 volts, and you'll see it regulating at 150 volts. Okay, let's just put this on. So I'm going to probe the rail voltage just here. Okay, give you the scope screen. Turn that one off, go back up to the rail. Oh, still 50 volts in the rail. Very, very low self-sync of the rails there. Okay, so there we go. We are all powered up. We have Class D switching, I believe. Yes, we do. And we have 151.7 volts worth of rail. So, that is regulated. As you can see, we have varying duty cycle on the power supply FETs. We go up to 12 volts. Based on square law correction, that should increase the rail, but of course it doesn't because it's regulated. So the power supply is now working less hard. We're at 12 volts there. Now, if I increase the voltage to 12.5 volts, again, we're still regulated at 150 volts, as you'd expect. Now, the way that regulation works in amplifiers is obviously to keep the rail voltage at a specified point here, 151.7 in this case. That means that when the voltage increases beyond 12.5, 13, 14, it should keep it at 151. Let's keep going. 12.7, 12.8, 12.9, 13 volts. So yeah, we're still at 151 volts, so we're still regulating. That's exactly still as designed. Now let's go a bit further. 13.1, 13.2, 13.3, 13.4, 13... Oh, hang on a minute, what's going on here? All of a sudden, we're no longer at 151 volts anymore, we're at 159 volts. That's very strange. Let's go back down again. Back down to 13 volts. Okay, now we're regulating. Okay, yeah, we're regulating at 151. So 13.5 volts. Oh, what the heck? We're now at 170 volts. What's that all about? Let's keep going. 13.8 volts at 193. 14.2 volts, 194. But now, even if we try and go higher than 14.4, it doesn't want it. Like, we're at 15 volts now. It doesn't go above 194. So we're now regulating at 194 volts. Let's go back down to 13 volts. Now we're regulating at 151. But as soon as we hit 13.5, as soon as we hit 13.4, 13.5, the amplifier allows higher rail voltage and it starts regulating again, but at a higher voltage point. Now, I have never seen that before. An amplifier have two different points, 2 different rail voltages that it will regulate at based on the input supply voltage. But I can see it making, I can't see it making sense, you know? Actually, no, I can't see it making sense. That doesn't make sense to me at all. So basically, the output power of this amplifier will be directly proportionate to the rail voltage. The more rail voltage you have, the higher voltage sine wave you can have on the speaker terminals, therefore the more power it can make. So when the amplifier here is connected to some kind of vehicle supply that is under 13.4 volts, this amplifier will be limited to a rail voltage of 151.7 volts, and therefore its output power will be limited. If this amplifier is connected to a higher voltage power supply, you know, if it, for example, you turn the engine on, now you're charging at 14, 14.4, 14.8, 15 volts, whatever the case may be. Now the amplifier is going to push the rail to its absolute maximum limit of about 195 volts, and the amplifier is now going to make as much power as it possibly can. That doesn't make sense to me. Why wouldn't you want the rails to stay higher when the voltage drops lower? The whole point of a voltage regulator in the power supply section, to me, is to allow the amplifier to produce as much power as possible at a lower voltage, while still allowing higher voltage to be given to the amp without it then overshooting its voltage limits. So most voltage regulated amps, even the Chinese clones of this and even the original Soundigital circuits, they will sit at 195 volts worth of rail with 12.5 volts, and obviously if you increase beyond 12.5 volts they'll stay there. That makes more sense, because then the amplifier is going to make the same amount of power whether you're at 12 volts or whether you're at 14.8 or 15 volts. So that makes sense. That's a regulated power supply. It's the same amount of power whether you're at 12.5 or 15 volts. It's going to try and make the maximum power that it possibly can based on the rail voltage. Whereas in this case, the amp is sandbagging itself unless you're above 13.5 volts. Now, you might think, that's a good thing, because if this is connected to some crappy vehicle power supply and the voltage is dropping, then that's going to help save the amplifier. No, it is not. It's not. Because by dropping the rail voltage when the voltage drops, you're actually making it worse, because you're bringing the AC sine wave closer to clip point, which is the reason that amps fail when the voltage drops, by the way. When your vehicle supply is fluctuating and your voltage is dropping into the 10 volts, the reason that typically that kills amps is because you end up hitting the rail voltage limit because it's sagged down so much, because your voltage has dropped so much. That's what kills it. So these regulated amps that basically max out the output section at 12 volts mean that if your vehicle supply does drop from 14.8 to 12 volts, actually you're not at any higher risk of clipping than you were when you was up at 14 volts. The only difference it makes is there's a bit more current through the power supply section of your amp than there was before. So dropping from 14.8 to 12 volts on regulated amps is not causing any issues. It's not dangerous for the amp in any way or anything like that. A bit more current is passed through the power supply section and obviously through your power wires, but at the end of the day, the amp's still going to make the same power. You're not going to be any closer to clipping than you were before. But in this case, if you drop below 13.5, then all of a sudden, you've lost 50 volts of rail. That's massive. That's huge. That's a very, very, very big drop in rail voltage. And if you were kind of getting close to your clip point at sort of 14 volts, if you drop under 13.5 and the rail is like whoop down to 150 volts, now all of a sudden you're hard clipping. You're hard clipping now because the amp's decided to drop the rails. And now Class D switching is stop starting, is stressing the output filter caps. Why? Unbelievable. I don't understand. This doesn't feel like an unintentional design flaw. The way that it locks into those two different rail voltages very specifically at specific voltages, it feels like an intentional design choice. It's been programmed to do that. I can't think what the thought process behind that was. Why? Why is it done that way? It doesn't make any sense. Yeah, it's not to do with duty cycle. It's nothing to do with like, the power supply can't regulate you know, 151 volts anymore because the voltage is nothing to do with that, because all the other amps that are the clones of this do it. All of them do it, and it's fine. If the voltage is so high, like 16 volts, that basically, you know, then the duty cycle just gets so low, and the power supply just sends a couple of little pulses here and there to prevent the voltage going above 151. It's not. This isn't been done because of a limitation. This is an actual active design choice, by the looks of it, and it's very strange. And we're going to try and stop it from doing that. I don't like it. That sucks. What I want this amp to do is I want this amp to hold the rails at maybe like 185 volts at all times. That would be nice. It's enough headroom. It's far enough away from the breakdown limits of these components in here for them to probably run safe. But it's obviously enough rail voltage for this thing to make some decent power, and I just want it to hold it there. I don't want it to be going on and off like that. So yeah, really, really strange. So this amplifier, Vlad, has a single positive rail voltage. It's a single positive rail. It doesn't have dual rails. It's just 150 volts, and so it has half rail on the speaker terminals to combat it, to make that. It's a full bridge amp though, so obviously it's twice the power that a normal half bridge 150 rail amplifier would have. That's not a bad idea, Larry. Change one bank of the power supply gates and see if it's there's the ringing disappears. Yeah, I could do that. Yeah, 100. I agree. 195 is far too close. So I want to change that. I'm going to change that regulation point so that it's lower than that to start with, anyway. Now the question I have, okay, is this kind of voltage regulation mode where it's, you know, where it's holding it at 150 and then it's allowing it to go up to 195. Okay. The MCU will be using the battery reference voltage to make that change, okay? In order to choose which voltage regulator mode it's going to work at, it's going to be using the 12 volt battery reference voltage for that, because obviously it's not going to be using the rail voltage as a reference for that, because the rail voltage is going to be stuck at 151. It doesn't know. You know, if the rail voltage is at 151, how's it going to know whether we're at 13 volts or 14 volts? So the MCU is going to be using the battery supply for that. And that's really good. That means that we can calibrate, we can create a fixed battery voltage reference for the MCU to see, to lock the MCU into one of those voltage regulation modes. So we're obviously going to pick the higher voltage one, the 195 one, but I'm going to knock it down a little bit to about 180, 185, around that mark. Now just keep it happy, keep it safe, keep it reliable. One thing that is interesting though, which I haven't really done too much looking into, so obviously the rail voltage of this amp is 195 volts. The voltage limits on these components is 200 volts, but on the scope it's much higher than that, which I don't know how, like, this is something that I need to learn more about. Okay, so if we probe the low side drain, okay, of the output section MOSFET here, I might actually need to get my my times 100 probe, because the voltage is very high. It goes off the screen here. So I'm just going to see if I can grab my times 100 probe. Is that this one? No. Where's my X100 probe? Donde está? Is it this one? Yeah, I think it's this one. Here we go. Yeah, I'm just going to plug in my X100 probe, which will allow me to go up to 500 volts divide on the scope, rather than 50 volts divide. So plug that in and then change the probe to 100. Helps if I actually select channel 1 yet. So I'm going to turn it down to 100 volt divide. So now instead of 50 volt divide, I've got 100 volt divide, okay, on the screen. So that's going to just give me a bit more space on the screen. So the rail voltage at 12.3 volts is going to be locked in at 150 volts. Okay, so I'm just going to power the amplifier back up again. And we can have a look together. Just going to put the safety glasses on. I really don't trust this thing with the rails being that high. Okay, so the amplifier is up and running. So we've got 152 volts worth of rail thereabouts, okay? So this is what the Class D switch wave looks like. Okay, it looks like this. So as you can see, the VRMS is 102 volts, right? And what I'm going to do is I'm actually just going to go ahead and clear the display readings here. I'm going to go for VRMS and V peak to peak. Okay, so the peak-to-peak voltage of this waveform here is 173 volts, which is obviously higher than the rail voltage. Okay, so the peak-to-peak should really be, it should really be 150 volts, but it's not, because the way Class D works, it's a little bit higher. It's actually a little bit messy. It's kind of jumping around a bit here. Now, if we go higher. Okay, let's just probe the other side to see if that's doing the same jumpy around thing. It's not, only this side's doing it. Actually, this is kind of jumping around a bit here. It's kind of growing and shrinking. Why is it doing that? 50, 100, 150. So we've got these locked in at 150. But there's a little spike. Can you see the little spike? Now that spike is higher than 150. So I'm worried that actually there's a bit of a spike that goes higher than the breakdown voltage limit of these components. I'm just going to grab a oscilloscope ground probe. I get so many questions, oh, where's your oscilloscope ground probe? So my oscilloscope shares a ground reference with my power supply. So that's how it all works. But obviously, there being a long ground path, there's noise that appears on the screen, obviously. So when I want to actually look at the intricate shape of the waveform exactly as it is on the board, I do need to connect a ground probe to give it a close by, nearby ground reference so it cleans the waveform up a little bit on the screen. So that's just what I want to do now. If I can find my ground probe somewhere. Let's have a look. Because there is definitely some ringing on the Class D, on the drain waveform. And I want to see whether that's actually there or whether it's just a byproduct of there being a poor oscilloscope ground. Come on, where's one of my little ground probes? Here we go, here's one. Right. So I just need to tack this on to literally anywhere on the board. And that'll work fine. So the ground reference is the same everywhere. Yeah, so I'm just going to tack that on there. So now we should get a really, really clean waveform here on the scope. Power this up again. So yeah, we've still got a bit of a spike there. So if I increase the voltage now so that it regulates at that higher point, you can see the spike is actually off the screen. The peak to peak voltage here is actually 203 volts. So yeah, it's like properly on the limit, or even like a couple of volts over the limit for the drive IC, for the output MOSFETs. I mean, the rail caps are fine; they're like sitting at 195, but it's like right on the limit, which is not ideal. Blake, yes. The rail voltage steps directly from one point to another, there's a little bit of a ramp in between where it's a direct ratio, where it's not being held at a regulation point. So from the 151 volts to the 195 volts, that ramp is a ratio based on the input voltage from the battery from the 12 volt side. But obviously it gets there very quickly. It's a very quick ramp up. I think from like 13.4 to 13.7 is like 0.3 volts where it ramps from one to the other. The only thing that worries me about the spikes though is obviously the MOSFETs are seeing that spike, and the drivers are potentially seeing a bit of spiking as well. So if the Class D is literally switching at 195 volts, I don't trust that there aren't little spikes, little bits of energy that are just breaking past that limit. So yeah. So we've got a few things to sort out here. We've got a few issues to correct. Now you've seen all of the weirdness with this. I haven't even got to the preamp circuit. I haven't even ran a sine wave through this amp yet, okay, at all, since I've had it. Haven't even tested the low pass filter, high pass filter to see whether they're accurate or correct. Haven't tested to see whether the sine wave is clean even. I've literally just found these issues and I was like, right, they need sorting first. So alright, so let's, what issue should we sort first? Let's first of all sort out the problem of the parasitic current draw. Okay, if you just joined, the first design flaw with this amplifier is that when the amplifier is connected to the battery in your vehicle, without even the remote connected, if the voltage is too high, you can see the fans come on, and they're just on at all times. So they're just draining your car battery. Love to see it. And even though it looks like they're not on when the voltage drops below, 14, they're still trying to run. And it's because the MCU is backfeeding voltage from the battery voltage sense pin through to the VCC of the MCU, which is then energizing a lot of other circuits and stuff. So even though the fans aren't spinning, the circuit is trying to come alive, which is drawing a little bit of current, which obviously is a parasitic current draw, which is going to drain your batteries, so you don't want that. So that's what we're going to sort out first. Before we do that, we need to get rid of the rail voltage in the amplifier because it's probably still sitting at 100 and something volts. So let's just do that real quick. Got a little 100 ohm 5 watt resistor here that I just touch on somewhere in the amp that has rail voltage present on it. So the rectifier here will do. There we go. Little spark, and we now have no more rail voltage. Probably. Oh, yeah? Still got 120 volts? How? Okay, there we go. She cometh down. There we go, 1.5 volts, that's fine. So the high voltage rail is gone. Okay, so what we need to do then, guys, is first of all to both fix, we're going to fix two issues with one mod. We're going to fix the issue with the parasitic current draw, and we're also going to fix the issue of the random stepped regulation voltage. We're going to do that by removing R53 here, and that's going to disconnect the battery terminal from the voltage sense pin on the MCU, which is the third pin from the end here. That will prevent voltage backfeeding through the MCU to the VCC pin, and that will also allow us to connect the VCC itself, which is a 5 volt reference. That will allow us to connect that to the reference pin for the battery voltage and calibrate our own voltage there for the MCU to see. So the MCU will think that whatever voltage we put on there is a reference to whatever battery voltage is going to be present. So that's going to basically fix the stepped rail voltage problem as well, because it must be taking the reference from that pin for the stepped rail voltage. So let's remove this from here. So it's a 473. No, it's not. It's a 472. 4700 ohm resistor. So I'm just going to knock that off its pad. Now what we can do is possibly we can connect that resistor to the VCC. Okay, so the VCC is here at 5 volts. So this pad of the resistor is going to be going along to, actually it's there, isn't it? That's very convenient. VCC is right there, and this pin, this one here, is going over to this pin of the MCU. So if I connect this resistor to this pad right next to it, literally the one right next to it, we might be lucky enough that we step the voltage down enough from 5 volts that we get a good reference voltage. I've no idea if we will. I don't know what the pull down resistor is that's pulling that to ground as part of the voltage divider. So we can find out together. Let's just put a little bit of solder on that pad there to help it settle. There we go. Bit of flux. And I'm just going to spin that over. And attach that resistor to the pad next to it. And that will connect VCC to the MCU reference voltage pin through that resistor. There we go. Lovely stuff. Now I doubt that that resistor is going to be the correct value. That would just be very, very lucky. So we're going to find out. So we're going to turn the amplifier on, turn the 12 volts on. As you can see, we don't have any more current draw. The fans aren't spinning anymore because we've removed that resistor. So what we want to do is we want to see about 3. We want the higher voltage limit, don't we? So we want to see probably about 3 volts on that pin there. So if we probe this resistor here and we apply the remote, we want to see about, I'm going to change my probe here actually, I've got my times 100 probe, so it's a little bit noisy. Let's put that over there for a minute. Switch that one over there. Let's put that one back in number 2. Put that one here. Okay, so we want to see about 3-ish volts on this pad here, so let's see what we get. Okay, unfortunately we get 2.1 volts, which is allowing the amplifier to power up. I wonder what rail voltage that's going to lock in the output section to. Should we find out? What rail voltage mode is that going to lock the output section into at 2.1 volts on the reference pin? So let's go along to the rail voltage here. Let's put the safety glasses on just to be sure. Okay, so with that resistor in place, this is now locked into the first mode. We are 151 volts worth of rail. Now, technically, if my theory is correct, if we increase this voltage to 14 volts, the rail shouldn't go higher like it did before. Yeah! No, it doesn't. Look, see? It's now locked into rail voltage mode 1, which is 151 volts. So we could leave it there. You know, if the customer wants ultimate reliability, like everything is kept well away from its voltage breakdown limits, 151 volts worth of rail voltage, that's a lot better. Okay, it's not going to be going into higher power mode when the voltage is increased. But we're kind of sandbagging the amplifier there a little bit, I feel. We can actually do a little bit of maths to see what kind of power we could expect and we have to assume that there's no voltage, no rail sag. Okay, so if we go to you can just type this on Google, like, if you want to find out RMS voltage calculator. Okay, type in RMS voltage calculator, and this is how you derive the AC sine wave voltage from a rail voltage. So we know that the rail voltage is about 151 point something. We're going to say 150, yeah, say 151. Okay, so if we look at this here, the rail voltage is the peak to peak of the sine wave. Okay, because that's what the sine wave can do. The sine wave can go peak to peak on here. But this is a full bridge amplifier. Okay, so that means that there is a sine wave on both speaker terminals, so the voltage across them is double that of each terminal. So just for simplicity, we can instead just use the VP, which is the voltage peak, which is half of the VPP. So if we have a look at voltage peak, we put in our rail voltage here for voltage peak, 151 volts, calculate. That is going to allow a 106 volts RMS sine wave across the speaker terminals with a full bridge amplifier. So now if we go to rapid tables and we do just the basic Ohm's law calculator, which you can do yourself without needing a website, but it's just easier to show you on the screen here. So we're going to type 106 volts in here into 1 ohm. That's going to basically, provided there's absolutely no rail sag, this amplifier will try to make about 11k. Okay, this amplifier was rated as, I think, a 13.5k. So we are sandbagging and limiting this amp a little bit by doing that. Now in reality, the rail voltage will have a little bit of voltage sag, because obviously as you're drawing current across the amplifier, it's going to sag the rails down a bit. But because it's going to be regulated at 151 volts, that means that it should reliably make, you should definitely be able to get the 11k out of this thing without any issues. Now if we increase the regulated voltage from 151 volts, say to like 180 volts, what will the amplifier try to make with 180 volts worth of rail? Now bear in mind, it's never going to actually make this because of rail sag, but if we pretend that there isn't any rail sag and we redo our calculations, so now let's do 180. So let's pretend the amplifier can maintain 180 volts worth of rail at all times, even under full heavy load. So we've got 127 volts there. So we just reset this, 127 volts into a 1 ohm load. The amplifier is going to try and make 16k. So obviously, as I've just explained, it won't ever make the 16k because there are lots of losses across the PCB, and the losses will get greater the more power it tries to make. So let's say if we keep it in rail voltage mode 1, which is the 151 volts, it probably will make 11k. Okay, if we step it up to the rail voltage mode 2, which is the 195 volts, which is what it's currently trying to do, or let's say we calibrate it to 180 volts, it's going to try and make 16k, but it might actually maybe be able to bench like 13.5k, let's say. So it will definitely be more power than it was able to do before, and also the fact that the rail voltage is higher, meaning the AC sine wave can be higher, means that it will sound louder with impedance rise, because you'll be able to get a bigger sine wave in there before it starts clipping. So it will do more power after rise with a higher rail voltage. That's one benefit of it. By limiting the rail voltage to 151 volts, we're basically giving it a fixed clip point there at 151 volts, and that means that even if you connected this to a system that had a lot of impedance rise, you might actually be losing out on quite a bit of performance there, because you're now hard clipping the amplifier, even though we're way far away from the amplifier's actual power limit there. So what we need to do then, in order to get this amplifier into the regulation mode 2, is to lower the resistance here. So we've got 472, so we've got a 4700 resistor, 4700 ohm resistor there at the moment. So we need to lower that. We need to bring the reference voltage up a bit higher. So let's have a look what I've got and see what we can put there instead. I will look at some of your guys' live chat soon. I'm just trying to kind of get through this while I've got some momentum. There's quite a lot of rail voltage still in the board, so I'm a bit scared to just drop anything on the PCB in case it shorts something out, but we should be right here. So what do we got here? We've got, no, it's too high. So I'm probably looking for maybe like 2200 ohms, something along those lines. 2700 ohms. Let's see what I've got. We've got 56, that's too low. So I don't have individual draws for each resistor because I don't have that many draws and I have a lot of resistances. So they're all just, I have categories. This category is greater than 100 ohms. So everything greater than 100 ohms goes in here. This is 27. This is 27k, so that's way too high. 1500, that's way too low. Although it might be right. 1500 ohms might be okay. That's 1000 ohms. 681. That's another 1500. Well, I'll just put the 1500 there for a minute. We could try that one. It's a fair bit lower, but it should get it into regulation mode too. So that'll probably work. 331. 6. So that's here we go. We've got 2000 ohms. That would work. These are a bit big. The package size is a bit large, but you know I'd make it fit. What else we got? Now obviously we could use a potentiometer as well. A potentiometer would allow the end user to maybe choose whether they're in like safe low voltage, low rail voltage mode, or turn it up to high rail voltage mode. That would be pretty cool actually for a competition. Like if you were competing with an amplifier like this, but you didn't want the rails running at 195 volts at all times, you know, just dailying, you were happy to have them sit at 150 volts, that would definitely allow this amplifier to be more reliable. So you could have it on like daily mode with a lower rail voltage, and then when you dropped into the lanes, you could just like turn up the potentiometer, which would then send it into 195 volt rails to give you absolute maximum power for your test. 1500 again. So that would be a pretty cool option. I might actually ask the client if they want that, if they would like that functionality or not, but I would advise against it. Probably. I think that fixing the rails at 180 volts would definitely be good enough for most applications. 2001. Here we go. Here's some smaller package 2000 ohms. So I'm going to drop a 2000 ohm in and just kind of see whether that gets it into regulation mode 2, the higher voltage regulation mode. So let's drop these back into the drawer, put these here, and yeah, let's just fit this resistor in place. So yeah, the voltages sound quite scary inside here. Oh, you should 3D print some resistor organizers. That's a very good idea. I'll definitely look into that. But yeah, the voltages sound kind of scary. 200 volts, but it's nothing compared to the Korean half bridge amps. You know, you get those like 10k, 12k Korean half bridges. The voltages in those things are 450 volts worth of rail. That's when it's terrifying. I hate working on those ones. That is so much energy stored in those rail capacitors. Yes, very horrible amount of voltage. 450 volts. Someone says, "Hey man, my name is William. Your videos have inspired me to start tinkering. Now I bought a scrap SD3K that is burnt to crap and has such a mess. I'm kind of lost." Wow, yeah, those things definitely can go down with a bang. Good luck with it. I think one of my videos that will probably help you quite a lot is probably going to be the how to fix clones. I've done like an hour-long repair guide on like the Brazilian clone amps, and obviously there'll be a lot of similarities with how you approach one of those to how you approach your 3K probably, so that might be useful to you. Right, so I've lowered the resistor in that voltage divider network. So now if we probe that voltage, hopefully we get something above 3 volts. And that's going to send this amplifier into rail voltage mode 2, which is going to be up at 195 volts. Now, I don't want it at 195 volts though, I want it a bit less than that. So in order to get it to regulate less than that, we're going to have to change the values of this voltage divider right here, which is what the MCU is using to sense the rail voltage. So to do that, I'm probably going to want a potentiometer in order to calibrate, you know, what kind of resistances I would need across that to make that happen. So yeah, but just to start off with, let's just see whether we have 3 volts there at our reference now, or there or thereabouts. Okay, we've got 3.1 volts, so that might be enough to trick the MCU into thinking that we have, you know, high voltage on the power terminals. So let's see. I'm going to start off actually with the voltage nice and low. I'm going to go down to like 9.7 amps. Sorry, 9.5 volts here on the power supply, and we're going to just start it up nice and low like that. And then when the amplifier comes to life and class D switching initializes, I'm then going to increase the voltage here and see whether it rises above the 151 volt hard limit that it imposes on itself. Okay, there we go. So we have, yeah, I mean, we've got a huge amount of idle current draw because of the issue with the power supply. So now, okay, no, are we still in? Okay, no, so the MCU is still in mode 1. We're still locked in at 151 there. So we actually need a lower resistor value there in order to get mode 2. Okay, let's try a lower resistor value. Yep. Turn that off. So what do we put there? We put a 2000. So let's put a 1.5K. Okay, so yeah, let's remove the 2000. Let's try a 1.5. Not that. That's a 1000. We could do that if we need to. Maybe I should just go for a 1000. I don't know. What do you think? Let's try 1.5 first. There's a 1.5. 273. Actually, you know what? Screw it. Let's just go all the way down to 1000. 1K. That should do the trick. That should just get it done, shouldn't it? Probably going to be at like 3.6, 3.8 volts, something like that. Okay, there we go, 1000 ohms. So again, let's power up and have a look at the rail voltage. I'm going to go back down to 9.5 volts there, so that we're nice and safe to start off with, where the rails have sank down to 131 volts. So let's just power up and see what we're saying. Okay, so we're powered up with 150 volts, so let's increase. No, we're still regulating, which is very interesting. We're still at 150 volts there. So we need even more voltage, right, hang on a minute. What reference voltage do we have here? We have 3.7 volts, that's very interesting. Okay, I guess we need even an even lower value resistor there. The VCC actually is dropped to 4.8 volts. Interesting. Perhaps the VCC supply isn't quite bulky enough to you know, to sync, you know, to get the voltage high enough. I don't really want to go less than I don't really want to start dropping lower and lower ohm resistors in here. We've got 1000 at the moment. Next one down will be a 470. But what I don't want to do is I don't want to cause there to, you know, mean that there's then voltage drop across the VCC. I don't want the VCC to then drop to like 4.5 volts. So what I might have to do is take that voltage reference from some kind of stable 12 volt supply somewhere else. Instead I could actually probably just raise the resistor to ground that's part of that voltage divider. So there should be a resistor to ground somewhere that is, you know, pulling that voltage down, and if I change that for something higher, then that should resolve the problem. Let's see if we can find that. I'm just going to dissipate the rail voltage inside the amplifier for a sec. Okay, all that gone? Okay, yeah, rail voltage is down at 4 volts, that's safe enough. So, okay, where is the other resistor to ground that's on the back of that? So we should have a resistor to ground somewhere connected there to ground. So let's just read the resistance. What do we have? What is the current resistor? We're looking for something around 1.6k. Yeah, 1.65. Okay, so we've got 1.65k to ground. So let's have a look. We should have some. So we need a resistor that has continuity to this one, and then ground on the other side. Possibly going to be around here. Nothing there. No, that's the rail. Okay, there we go. We've got a resistor right there. And do we have ground on the other side? Yes, we do. Okay, there's our resistor. And that's actually a 332. So we can drop that. Let's try dropping that to a 2K. That might just be enough. So that's currently a 3300. So if we drop this to a 2000, that might be enough to bring the amp up into rail voltage regulated mode number 2. Okay, let's see what that's done. So we had 3.7 volts on the reference earlier. So let's just see whether we still have roughly that or not. So VCC is up at 4.8 volts, that's fine. The reference voltage for the MCU is now at, oh, what the heck, 3.2. Oh, I'm an idiot. I made the resistance lower. I need to make it higher. What am I doing? I'm sure some of you probably said that in the chat just now, but I wasn't reading it because I was busy. No, we need to make that higher, obviously. What am I doing? So we had a 332. So let's see if we can put a 472. That would work well. 4700. Let's see. Do we have a 4700 somewhere? What was the original one? I feel like the original resistor was 4700 that we had in this place here. So what did I do with that? Did I remove that and put it on the table somewhere? Just be handy if that was like laying around somewhere, which probably it's not. Probably lost that, never mind. Okay, so let's look to see whether we can find, might just grab one off of this donor board. this one's been burnt to a crisp, so it's very hard to see the resistor values. I'm looking for 472 or 4701. Do we have 27, that's too low. Come on, 472 or 4701. Lots of 332s, lots of 222s. Come on, where are you, 47? Why are there no 4700 ohm resistors on this board? There's like a super common value. Okay, let's try something else. Do I have one in my drawer? I feel like that's a resistor value that I've always just grabbed from a donor board, so I probably don't have one in a drawer somewhere. 4751. That would do. It's a bit big though. That's a very large package resistor, but that would probably do. 14k, 182, 1500, 2200. Alright, let's just use one of these large package ones and just scoot it onto the pad. It'll be fine. It'll be fine. So for anyone who's recently joined, a quick recap of what the heck we're doing with this board. This is a unbranded prototype, I guess. This is a clone of the Soundigital circuit that has been manufactured in a Korean factory. The first one of those that I've seen. All of the other boards that look like this come from China. Chinese cloning the Soundigital circuit. This is a Korean one. Client bought this, I think, from Alibaba or something like that, or some other website where they're selling factory direct. And it has a whole bunch of design flaws and problems. Firstly, it was causing parasitic current draw through the amplifier when the remote was not even connected. It was trying to power the MCU and also trying to power the fans even when the remote wasn't connected. So that's design flaw number one. Design flaw number two is that there is not enough dead time on the power supply MOSFET gate drive. So the amplifier draws about 13 amps at idle and the power supply MOSFETs get very hot. It's either a lack of dead time or it's an incorrect switching frequency. We don't know what one of those it is for sure just yet, because we need to do some mods to find out which one of those is the problem. The third weird thing about this is 4750. The third weird thing about this amp is that it was regulating the voltage, the rail voltage, to 150 volts. Under 13.5 volts, and as soon as you went above 13.5 volts it would then suddenly start regulating the voltage to 195 volts, which doesn't really make any sense. It's kind of backwards. You want to make sure the rail voltage is staying at the regulation voltage, the highest regulation voltage at all times. So yeah. Alright, so now we've got the 100 and the 1500 ohm resistor fitted on the pull down instead, so that should now result in a higher reference voltage for the MCU. So let's have a look. Okay, MCU reference voltage is now 4 volts. Okay, that's the highest we've seen so far. 4 volts. So if that doesn't get this amp locked into rail voltage regulation mode 2, then I don't know what will. I guess we could just connect it straight to VCC. Just, you know. Okay, let's start off nice and low on the rail, and let's just probe the rail voltage here. Let's just, hopefully we get to... Ah! Well, that's very strange. Now the amplifier is complaining that the voltage is too high. It's now in protect. It's flashing the blue LED. Bleep, bleep, bleep. Oh, you can't see that. Okay, but okay, just trust me. The amplifier is now in protect because the voltage is now too high. Okay, so that means that would suggest that it's not using that reference to switch between the two rail modes, but it must be, because when we tied it to VCC, it locked itself into rail voltage mode 1. So what is it that gets it into rail voltage mode 2? Is it just that the voltage, the 4 volts, is a bit too high? Is it just that there's a very, very tiny, there must be a tiny window of voltage between 3.8 and 4 volts where it's in that window of being in rail voltage mode 2, but not so high that it protects. So I'm going to change this resistor, this 1K. I'm going to change this for a let's try putting the 2K back in place and see what that does. This is the 2K. Okay, so I'm going to put the 2K back in place. Okay, so that's the 2K back in place. This is probably going to be where we need a very, very specific resistance value. Like a potentiometer would be great here, or a trim pot, as you will. Alright, so what does that give us? That gives us a reference voltage of... See, that's 3.4 volts. That's not going to be enough. That's just going to lock us into rail voltage mode 1, as we already know. So we need like something between... Alright, let's try my 1500 ohms. I might have to use a voltage divider calculator here just to get two resistors that are perfect. Where's my 1500? Actually, I bet there's a nice cheeky 1500 on this donor board. Uh, 1501, 152 we're looking for. 111, no, what if I fucking... nope. It appears there is not. There's not a 1.5 anywhere to be seen. Okay, no worries. Ah, William with a 5. Dude, thank you so much. Thanks for your tip, to your video. Definitely going to watch it. I got a Google Drive folder, or of the horror if you'd like to see it. Yeah, man, absolutely. Yeah, feel free to share the link either publicly here or on my Bearvidge Facebook page. Facebook.com/Bearvidge. If you want to show me the pictures, I'd love to see it. I could maybe give you some pointers. But thank you very much for your generosity with the 5. That's massively appreciated, buddy. I appreciate you. Thank you very much. Can't find me 1500. Where have I put it? Here we go. Here they are. All right. Drop you on there. I think I need a bit more flux because we've done this a few times now and it's a bit dry. There we go. Okay, that's 1500 fitted. So what voltage do we get now? Please, I want to see like 3.9, I think. That would be great. If I can see like 3.9, I think that would be nice. 4.8. Ah, that's because that's not a 1500, that's a 150. Okay guys, I think I'm a bit too hungry to be to be doing this just now. So I think thanks for joining. We're going to lock off the stream here. But hopefully this has been interesting for you to see what kind of weird problems this has got out of the factory. Rubbish, unoptimized, not checked properly, not R&D. This is just a slapped together piece of junk from a Korean factory copying the Soundigital circuit. I will continue with these mods, probably in a later stream perhaps, or maybe I'll do a video about it or something like that. But I hope that's been interesting for you. Thank you so much to everyone who has commented in the chat here. I'm just going to skim through just if there's anything to answer here. It's like old school injection system tuning by changing resistors around. Yeah, it feels a bit like that for sure. I'm super behind. Yeah, there's a lot going on here. Any smart repairs? No, not yet. Not yet, bro. Coming soon. Would you have these issues if you ran the amp at 2 ohms? Yeah, you'd have them more. This would be more of an issue because you'd have even less headroom before it hit clip. Dinner was cancelled immediately. Well, go make some dinner now because I'm about to go make some dinner. Yeah, there was enough flux left over from when I fluxed it originally. I've heated it like 4 or 5 times and the flux kind of buggered off, so I just put some fresh one down. But yeah, guys, thank you very much for sticking with me for this one, and I hope that was interesting, and I'll see you next time. Enjoy the rest of your evening. Bye bye.